Okay, we are going to look at some important properties of rational expressions. So remember, a rational expression is just where you have a fraction, the numerator is a polynomial, and the denominator is a polynomial. Okay, so rational expressions, rational functions. So here's the thing about them though. We've been dealing with polynomials which are really nicely behaved, smooth, continuous curves. Rational functions overall kind of behave like that, except where they don't, right? So you can get some discontinuities with rational functions, and you can get some other kind of weird behavior. So we just want to look at those kind of behaviors so that we know how to treat the special properties of a rational function. So one of these things occurs where your rational function is undefined. So let's take a look at this first rational function right here, x minus 3, x plus 4. Now, one mathematical concept that I want to remind us of, because it's going to keep coming up whenever you deal with rational functions, you kind of want to call up this idea and keep it in mind because it's going to help you keep things straight. So when you have a fraction, think about the numerator and the denominator. What happens to a fraction where you hold the numerator the same, but you blow up the denominator? You make it bigger, 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 right? Well, as that denominator grows, the whole fraction shrinks down, right? It gets smaller. So denominator getting bigger makes the fraction get smaller. Numerator getting bigger makes the fraction get bigger. Likewise, denominator getting small makes the whole fraction bigger. Okay, so you want to be able to think in terms of, all right, if I have a fraction and I change the numerator, what does that do? Does that make the whole fraction bigger or smaller? You want to be able to play that game. Okay, and so here's the first place that this comes up. Let's take this fraction right here, x minus 3 over x plus 4. Well, look what happens at negative 4. When we plug in negative 4 for x, we get 0 in the denominator of a fraction, and remember, that's not allowed. So at negative 4, our first function right here is actually not defined. But we get some weird behavior around x equals negative 4. So if I put this in here, we're going to call that a vertical asymptote. And see what happens where the graph comes over and it starts getting really close to this line but never touching it. And it's doing the same up here. It's getting close to this line and never touching it. That is a vertical asymptote. And they occur where your denominator is undefined. And here's why. Think about the values as they get close to negative 4. So what about at negative 3.999999999? Well, negative 3.9999999 plus 4 is a really tiny number. It's like 0 point, a bunch of zeros, 0.0000001. Right? I don't know if I got the right number of zeros in there, but you get the idea. It's a really, really tiny number. So what does that mean? That means this whole fraction is some reasonably sized number over a really, really tiny number. And like we just discussed, that's going to make the whole fraction blow up, get bigger. So that's why you see this behavior where it starts shooting up towards infinity. And over here on this side, it's shooting down towards negative infinity. That's the behavior that you get right around a vertical asymptote. And again, it's because at the point that you're undefined, you're getting 0 in the denominator. But right near that, you're getting really, really tiny numbers down there. That's where vertical asymptotes come from. So all you have to do then is figure out where your denominator is equal to 0, and then you solve that. So you literally just set your denominator equal to 0, and the places where you solve that equation, the solutions that you get, that's where your vertical asymptotes are occurring. All right, so you can see, like in this case, if I plug in negative 4 to this denominator, I get 0, and notice that my vertical asymptote is x equals negative 4. Now, there is a caveat. I want to be careful. The work that I'm telling you, that's about an already simplified fraction. So it's assuming that you've already canceled out common factors from the top and bottom. Because remember, when you have a common factor in the top and bottom, that actually shows up as a hole in your graph. We're assuming you've already canceled all of those out. And if you still get 0 in the denominator of a fraction, then you get this kind of vertical asymptote right here. Okay, well, that's real easy to see in this case where we get negative 4 in the bottom of the graph. But what about, or in the bottom of so that's really easy to see here that we get negative 4, because it's really easy to see how you get 0 in the bottom of the fraction, giving us zero, undefined, so that we have a vertical asymptote. Well, what about when I have more complicated expressions in the denominator? Well, it's the same thing. You just set them equal to 0. So x squared minus 49, well, we know that that's really x plus 7 and x minus 7. So now we can see and go, oh, I'm going to have problems at 7 and negative 7. Watch, because if I plug in negative 7, it makes this part 0. If I plug in 7, it makes this part 0. So let's look. Let's see where those... In fact, let's go ahead and graph them ahead of time. Right? This is our prediction that we know where those vertical asymptotes are going to be. And let's see. Yep, sure enough, they're right where we predicted them to be. You can see this behavior showing up right here. So we see we've got 2 vertical asymptotes, one at each place where the denominator is equal to 0. So it's really just that simple. Take your denominator, set it equal to 0, solve it, and you're going to get your vertical asymptotes. Okay? So that's what we have for vertical asymptotes. So now notice that we have something here that we call a horizontal asymptote. So the horizontal asymptote, you can kind of look, is occurring right around, it looks like it's right around at y equals 1. So now we have it in a horizontal dimension where the curves are coming up and they're getting close to this curve but never quite actually touching it. Where does that horizontal asymptote come from? Right? How do we figure out what that is? Well, there's 3 cases for the horizontal asymptote, and the good news is they're easy to figure out. Now, this is a case where I see a lot of students trying to memorize this, and then they get confused and they mix them up. Don't memorize it, just understand it. Just understand what causes the horizontal asymptote to occur, and then you won't get confused. You'll just understand it. So there's 3 cases. The first case, the case that we're looking at here, right? So I'll rewrite this as x squared minus 49 as I had it. In this case, the degree of the numerator is equal to the degree of the denominator. So remember back when we talked about the leading coefficient test and we said that leading coefficient is really calling the shots, meaning that in the grand scheme of things, right, the horizontal asymptote is really about end behavior. So when we look at the end behavior, this 25 and this 49 are not really playing much of a role. They do around in here. They give us our vertical asymptotes and they give us, x-intercepts and stuff like that. But if we're trying to figure out the end behavior, which in this case will involve a horizontal asymptote, we're looking at those lead coefficients here. If the lead coefficients in your numerator and your denominator are the same degree, then it's going to be the ratio of their coefficients is going to be your horizontal asymptote. So in this case, it's 1 over 1, which is 1. So that's why we got y equals 1 down here as the horizontal asymptote. So we can see we've got y equals 1 right here. If I change this to 2, and maybe I make this a 3, then our horizontal asymptote would be at y equals 2/3. And sure enough, if we zoom in, it looks like that's the new value, right? It's coming in and coming along right at y equals 2/3. So it's the ratio of those coefficients if the degree of the numerator and denominator are the same, because those 2 leading coefficients are sort of fighting it out, but they kind of have the same strength. So it just ends up being the ratio. Okay, well, what if you have a bigger degree in the denominator, like this? Okay, well, in this case, we get kind of a weird graph, but it looks like our horizontal asymptote is actually the x-axis. And that makes sense because think about our lead coefficients. This cube term is going to grow way faster than the entire numerator, which means we have that growing denominator, which shrinks the whole fraction. So that's sending everything down to 0. So we can see we're approaching 0 on this side. We can see we're approaching 0 on this side. And this graph actually does a good thing of illustrating an example that sometimes people kind of get confused about because they're lazy with their language. So sometimes you'll hear people say, oh, the graph can never cross a horizontal asymptote. The graph can cross a horizontal asymptote, but it can only cross a horizontal asymptote in the middle of the graph, like around the x-intercepts and the maxes and mins and all that kind of stuff going on. Once you get locked into that end behavior, once you've traveled far enough away from the middle, you're not going to cross that horizontal asymptote anymore. You're just going to forever get closer and closer to it, but never quite touch it. There's this ever shrinking distance between the asymptote and the curve itself once you get away from the middle of the graph. Okay, so that's how you get 0 for your horizontal asymptote. And what happens if the degree of the numerator is bigger than the degree of the denominator? Well, that means your numerator is going to grow. Well, that means that your whole fraction is going to grow. And what that means is you don't have a horizontal asymptote. At that point, your end behavior, it will be like a polynomial where it's either going up to infinity or it's going down to negative infinity. One of those on the ends, right? So that's your 3 situations, and again, you don't have to memorize it. Just understand that whole idea of, if I change part of a fraction, does it make this part bigger or smaller? And you can just reason your way through what the behavior is going to be for a horizontal asymptote or not.